This is the 2-4 notes for Calculus 1. So there are going to be, the next two sections we're going to concentrate on limits that are a little bit different. So there are two types. There are what's called infinite limits, which we cover in this section, and limits at infinity that we cover in the next section in 2.5. Now, note that these are completely different things. I know that sounds weird, but they look like they're saying the same thing, but they're actually not. So before I do anything, I just want to be clear on the difference between them so that you can see, you can kind of get an idea of what one means and what the other one doesn't, essentially. So what are infinite limits? So infinite limits are, you're going to have x approach some arbitrary value that you normally do, like 0 or 5 or 7. But when you actually determine the physical limit itself, whatever that function value, whatever the height is, it turns out that that value ends up being positive infinity or negative infinity. So essentially, the limit increases or decreases without any bound. It goes on forever. So that's what we'll be doing in this section for infinite limits. So just as sort of a preview, so what does that look like? If you look here, so the limit of x approaches some value, it could be 5, it could be 8, it could be pi, whatever it is, of the function. The answer is actually going to be infinity or negative infinity. That is an infinite limit. Now, just to be clear, what is a limit at infinity so you know what you're not doing? So instead of x approaching an arbitrary value like 5, 7, -2, whatever, instead it's going to be approaching infinity or negative infinity, which means basically on the axis, of the x-axis, you're, instead of approaching some random value, it's going to be approaching all the way that way for positive infinity or all the way left for negative infinity. So we don't have to get too much, I don't want to get into much detail with that now because we have the whole next section, but that is the difference between these two sections in terms of limits. Okay, so let's talk about a good example, a very common example of an infinite limit. So look at this guy right here. So we want to find the limit of x goes to 0 of the graph 1 over x squared, or the function 1 over x squared. We're going to use a table and a graph to do that in terms of what we're doing, because I want to make sure that you clearly see what's going on. So what I did was I made a table. So here's your function 1 over x squared, and I have a bunch of x's to plug in for it. So what I did was I started with positive 0.1. So if you put 0.1 in for x here, you're going to get 1 over 0.1 squared, which is going to give you 100. Now note, whether you put in positive or negative 0.1, you're going to get the same result because you're squaring x. Then I did the same thing for one more decimal place, 0.01. If I sub that in positive or negative into 1 over x squared, I get 10,000. What about one more decimal place? I'm going to get 1,000,000 if I sub that in. Okay, so what is actually happening? So the values of x that I'm listing are clearly heading to 0, quick. But what's going even faster, the value of f of x is going towards an arbitrarily large number. I mean, look at these numbers here. They are getting big fast. So what is that implying? That's implying that these numbers are heading to infinity. So that is going to be sort of the key in terms of what we're doing. Now, what does that look like on the graph? Well, if we're heading towards 0, so what do we normally do? So this limit is a two-sided limit. So we would take it from the left and the right. So the red arrows here represent, the ones that are on the picture, I'm blurring blue, represent moving towards 0. So what is happening as we're moving towards 0? We're following this line, but look what happens as we follow. We don't actually end at like a value. We actually just keep on going forever in the up direction, knowing that we never actually get to 0. So we could keep on going blah, 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 all the way up here, too far. But we're actually never going to cross the y-axis, which means we're heading, in terms of a height, we're heading to infinity without bound. So what about on the other side? Well, same thing. If we start coming this way, trying to get to 0, which we'll never get to, we get directed in this up direction to infinity, which means the limit as x approaches 0 of 1 over x squared is equal to infinity. Okay, that is the key concept here, and hopefully you kind of understand that that is what's happening. There is no height that you're actually approaching. Okay, so let's look at an example. Let's say we have this crazy rational function right here. So all we're going to do is we're going to use the graph to sort this out. I'm going to be using an analytical way at the end of the lesson, which is going to be very valuable and will help you understand the whole process. But for now, I'd like to just look at the graph. So the graph is over on the right. It looks very funky, but let's talk about, what these limits look like. So I need to take, letter A, I need to take the limit as x approaches 1 from the left of this function. Okay, so the value 1 and 3 are here and here. So I need to approach 1 from the left side. So that appears to be right here. So I am going. I'm trying to approach 1, but where is it pushing me to? The height is being pushed to positive infinity. Okay, so if we're being pushed to positive infinity, this is clearly an infinite limit. Now, what about B, which is right below it, 1 from the right side? Okay, so it looks like if I'm trying to approach 1 from the right, I am being, again, pushed where? Towards positive infinity. Okay, an interesting byproduct of that is, what does that mean the two-sided limit of those one-sided limits will be? Well, since they're both infinity, we can say that the limit of x approaches 1 is officially infinity, positive infinity. So that actually would be the answer. Okay, let's try another set. Let's say we're at 3. It says the limit of x approaches 3 from the left side. All right, so it looks like if we had tried to approach it from the left, where is it being pushed? It's actually being pushed infinitely in the negative direction. So the limit as x approaches 3 from the left side is negative infinity. What if we approach it from the right? If we go this way, right, where are we being pushed? We're being pushed infinitely in the positive direction, so we get positive infinity. But what if we need to find the two-sided limit? Take a peek at these. Do these agree? Are they the same? They are not. I don't use the word equal because infinities don't actually have values. It can't be equal. But basically, are they the same limit? They are not, which means we are right back to this result. Technically, it's not equal to d, that does not exist, so I put a little arrow on this, but basically it does not exist, the two-sided limit. Okay, last piece here, and this is a pre-calculus blast from the past. It says, what are the equations of the vertical asymptotes? Okay, so here we are. If you look at the picture, I have clearly marked these asymptotes in a purple color, but if you have your printout, it's probably not a purplish fuchsia color, but basically they are dashed. So if you look at these, hopefully you understand that these are the asymptotes of this function. Okay, they are values that the graph approaches but will never cross. So what are the equations of these? Well, remember, horizontal lines have the equation of y equals some number, but vertical lines have the equation of x equals some number. So therefore, this equation is going to be x equals 1, and this asymptote equation is x equals 3. So I am picky with this. When I say what's the equation of the asymptote, don't say 1 and 3. Those are not equations. These are equations. Y equals mx plus b, y equals something, x equals something. Those are equations. So what is the actual equation? X equals 1 and x equals 3. So just a note up right here, it says you might have noticed the functions featured predominantly in this section are rational functions. Another word for rational, again, is fractional. Okay, just in case you are forgetting that. Which just so happens to always have vertical asymptotes. Or not always, but usually has vertical asymptotes. Recall that vertical asymptotes are found by setting the denominator of a factored and simplified rational function equal to 0. Okay, so let's just be clear with that. So look at this. So everybody see this function. note that there's no way we can simplify this. It is fully factored already, which means what do we do in order to find the asymptotes? We take the denominator and set it equal to 0. So how do you do that? It would be, you would set x minus 1 squared equals 0 and x minus 3 equal to 0. Either one gets the solutions x equals 1 and x equals 3, which are right here. Those are your actual functions. So what about this guy here, right? What about 1 over x squared? Well, the denominator, you set it equal to 0, and you get x is equal to 0. Well, look at the asymptote in this problem. It's at the vertical line, x is equal to 0. So I just wanted to show you that so that you have a good reminder of what we do with vertical asymptotes, but let's also talk about a nice formula that we can now conclude because of it. Definition. It says, if you can find that this is the two-sided limit, or either one of the one-sided limits, so right-sided, left-sided, if you can find that as x approaches a, either two-sided, right-sided, or left-sided, any of them, if any of those limits are positive and negative infinity, you can immediately claim that x equals a is the vertical asymptote of the function. Okay, so just note this a is right here. Look at that. So how do we apply that in this example up here? Let's look. Let me get rid of some of the noise here. Okay, so we already have a lot of the solutions that are going on here. So if you're looking at this picture right here, if you can prove that the limit as x goes to some value, so this is a left-sided limit, if you can prove that that limit is equal to infinity, then that means that x equals a, which is right here, is a vertical asymptote. Well, look what we did. Didn't we prove that that limit is infinity? We did. So that means x is equal to a, which is 1, is a vertical asymptote. Hey, look at that. It is. What about over here? We took a right-sided limit and proved that the right side is equal to infinity. The limit up to the right side is equal to infinity of 3. So what does that mean? That means since we proved that a right-sided limit is equal to an infinity value, that means x equals a, 3 is a vertical asymptote. Hey, look at that. So this formula actually proves vertical asymptotes for you. So that's the point of it. So just note, that doesn't mean though, and this is the hard part, that doesn't mean that all of these limits are going to be infinity, because look at this guy. So even though this two-sided limit did not exist, this was still a vertical asymptote. So what it's basically, the key word here, let me get rid of all the noise. The key word is or. If you can prove that either a two-sided or either the one-sided or any of the one-sided limits are infinite, that automatically proves that x equals the arbitrary limit value, a, is the vertical asymptote. Number 2. Find all the vertical asymptotes x equals a of the following function using what you learned in pre-calculus. Then use a graphing utility to prove each vertical asymptote exists. Okay, so we actually are going to be doing a little bit of technology, because we're going to be using Desmos, which is a website on the internet, in order to do that, because I want to give you an option for printing out graphs and such. So we'll do that in a second, towards the end of the problem. But we first have to return to wonderful pre-calculus and talk about how we find the vertical asymptotes of this problem. Okay, so if you recall, it says right here, recall the vertical asymptotes are finding by setting the denominator of a factored and simplified rational function equal to 0. Okay, so what's the first thing we have to do in this problem? We have to factor and simplify. So hopefully the warning bells were going off already in your head that you need to factor this, because it looks like a factoring monster. So factoring the top here, the numerator, We need values that multiply to get -2 that have a difference of +1. That's x plus 2, x minus 1. The denominator, worth noting, has a GCF in it. Now, always look for a GCF. If you try factoring what's there, then algebra skills are probably a little struggling a little bit there. You need to factor out the x, and if you do that, then you can factor this. So you're looking for factors of -6 that have a difference of -1. That's going to be x minus 3 and x plus 2. Okay, so once you get to this step, what is the key? The key is that you must simplify. I'm not going to cross things out so I can't see them, because I need to see them for what I'm going to do later. But generally, this is what happens. The x plus 2's will cancel out, and you will end up with x minus 1 over x times x minus 3. Now, this is what you're not used to doing. So in pre-calculus, you wouldn't have done this, or in algebra. What do you want to do? Well, by doing this elimination right here, there was one thing that was eliminated that is valuable for graphing it. So whenever you eliminate, whatever the eliminated value was, is the whole in the graph. Everything else is the asymptotes. So here, what I'm going to do is I'm going to write vertical asymptotes. Right? Vertical asymptotes. Here, this is the whole. So whatever cancels out. So I'm going to write with a comma, x is not equal to -2. And then I'm going to make a note that this is the whole in the graph. So I'm going to show you that later when we're actually looking at the picture so that you get a good idea of like what the issue is with the graph. Because Desmos will not show the whole. But this literally is the proper concept here, like right here. So when you write it, you go, it's x minus 1 over x times x minus 3, but, comma, x cannot be equal to -2. That is sort of the key for the problem in writing. Okay, so we have the whole. What are the vertical asymptotes? So going down here, let's change color. So we said x times x minus 3 equal to 0, which means that x equals 0, and x is minus 3 equals 0, which means x is 3. So our vertical asymptotes are x equals 0 and x equals 3. Our problems. Okay, so that was all they wanted in the problem. Now, they didn't want the whole, but it's important that I point it out so that if you get a problem some point that you're adding them to your picture. But what the whole point of the problem was to show the vertical asymptotes using pre-calculus, and we did that. That's done. The second part of the problem is using technology in order to prove that these limits are what they are. So what do we need to do in order to do that? Well, if we need to, let's say we need to prove that x equals 0 is I'm going to do VA for vertical asymptote, okay? So let's say that's our first step. So what do we need to do? According to this theorem up here, we just simply have to prove that I usually just do a one-sided limit. You have to prove that a one-sided limit approaching x equals 0 is infinite. So let's just take one of the, like a random value. So one of these. So let's just do 0 from the left. Does it matter? No. But let's just do that. So we have to prove that this function, when it approaches 0 from the left side, becomes an infinite limit. What do we have to? We're also going to have to prove that x equals 3 is a vertical asymptote. So we have to prove the limit of f of x as x approaches. Let's just do 3 from the right side, just to do something different. I usually pick one-sided limits because sometimes the two-sided limits don't exist, so I try to stay away from them. And we don't need that in order to do the problems anyway. To find the two-sided limit, you have to do one sides anyway, both one sides. So why not just take one of the one-sided limits and prove it? So we basically need to do this in order to accomplish that. So let's head over to Desmos, and we will figure out how to graph things. Okay, so this is Desmos. If you go to desmos.com/calculator, which you see over in the web address at the top there, what it allows you to do is, it's not great for tablets, but if up in the equation guy over here, what it allows you to do is it allows you to type using the bottom of the page right here. You can see all the nice little mathematical stuff. It allows you to type in this equation and find the graph for it. It's actually pretty neat. You can do multiple graphs, so like you can double click here and put in a new graph if you want to. We're not going to do that, so you can have multiple graphs all over the place. You can also, and my type, by the way, my keyboard's going to keep coming up because it's not very good for the site, but I'm going to show you one other thing. So if you click on functions, it actually gives you all the different types of functions. Like you can see logs in here, you can see exponentials, there's some calculus stuff. They give you trig functions here, so it actually provides a really nice way to just simply graph functions. But what it doesn't do, as I stated before, is it doesn't put holes in the graph. So if you look back at our problem that we actually had a hole at x equals negative, not equal to -2, right? So what I'm going to do real quick is there's a clever thing in my tablet here that allows me to do a full screen snip. So now I can actually draw on the sucker. So if you look at this, this is the output that we had on the graph. So just returning to our problem itself, where are we? We're here. So remember, we had a hole at -2, right? And we had asymptotes for this guy at 0 and 3. We're going to prove that in a second, but I just want to show you the Desmos business. So if you go to the snip and sketch stuff, you can see at -2, which is right here. Let's do black right here. -2 right here, there is no hole in the graph. So if you were giving me this on an assignment, I would expect this big hole right here on the graph after the fact. So I'm just showing it to you. Also, you can clearly see that we have our asymptotes, right? So the asymptotes are actually here, and they look like they're at 3, which is right here on the graph. So you can see that the graph shows up really nice, right? And that's what you would add to your graphs if you were handing them in to me, by the way. Throw the asymptotes on there, throw the holes, but generally, what are we trying to prove using the asymptotes? Like, what is the point of this entire process? So what we want to do, basically, is we want to look at this and go, all right, let's prove, so going back to our problem, let's prove that x equals 0 is a vertical asymptote. So we want to prove, using our picture, that the limit as x approaches 0 from the left of the function. Okay, so if we go to the left of the function, we go, all right, well, 0's here, so if we're doing that, what are we doing? We're going along this line right here. And what is it actually pushing us towards? It's pushing us towards -infinity. So we go back to our notebook and we go, well, just from our picture, we have proven that this is a infinite limit, specifically a negative infinite limit. Therefore, we have just proved that x equals 0, which is our a, is a vertical asymptote. That's it. That's all we have to do. So similarly, if we go to our sketch here, we're trying to approach 3 from the right this time. So there's lots more colors in this. So if we're approaching 3 from the right, look where it's going. It's actually pushing us up to positive infinity. So that allows us in this scenario to say that this is equal to positive infinity. And since we found that a right-sided limit is equal to infinity, then x equals a 3 is a vertical asymptote. So that is the proof procedure. Sometimes you'll have a graph, sometimes you'll have to do it analytically, but I purposely made the graph so that it makes life a little bit easier for you to go through and understand, like, how do you actually do that. Okay, so we move on to the last part of our section, and that is finding analytical ways to determine limits. So what does that mean? No tables or graphs. There won't be any algebra normally in this either. It'll all be about using a method that I learned long ago that I'm going to pass on to you guys in order to determine an infinite limit in a pretty straightforward way. But before we do that, we're going to read here. It says when determining the limit of the fraction a over b, which is of course a rational function, if a remains non-zero and constant, in other words, it's a constant that's not zero, and b approaches zero, you conclude that the fraction a over b grows arbitrarily large. So it says it's important to note that the positivity and negativity of the fraction is also important in determining whether the fraction approaches infinity or negative infinity. Okay, so what does all of that mean? So this, basically, if you have a limit, when you plug in the number and you end up with a limit that, let's say, 2 over 0, then that means that it's going to be an infinite limit. Okay, we'll get into the details more in a second. Now, what have you already learned? You've already learned when you plug in a value of a, whatever it is, into my function, and I just get a regular number, then that's the limit. If I plug it in and get 0 over 0, then that's an indeterminate form, and now I have these other ways to figure out what the limit is. So now you have a new one, which is sort of a mix between the two. What if you have a constant over 0? That automatically means that it's going to be an infinite limit, and that is something that you always want to make sure that you're paying attention to, even in the most basic problems. So the key is we're going to use this concept and a very interesting little method in order to do the problems below to determine infinite limits. Okay, note that this method needs practice, right? This isn't something where you're likely to get this on the first problem. So if you're a little, lost a little bit as you go, that's okay. The goal is by the time we get down to number 7, you are pretty solid on what you need to do whenever you see this. So the key is, right now, to be clear, if we plugged in, so it says the limit is x limit of x approaches 0 from the right side of 4 plus x over x. If we plug in 0 right now, we get 4 over 0. Okay, so that means that we have a constant over something approaching 0, which is an infinite limit. Okay, so the key is that we need to verify that, which I'm going to show you in a second. But when you're doing a problem, if you get a constant over 0, you automatically know that you're dealing with infinite limits other than the other stuff that we were dealing with. So let's see how we break this down. So what you want to do is you want to isolate the function, which is 4 plus x over x. What we want to do is we want to talk about what each one of these numerators and denominators are actually approaching. So in the numerator, if you plug 0 into the function, or a value that is to the right of 0, a small number, you're going to get basically a function that's approaching positive 4. Positive 4. Okay? What about the denominator? Well, if you plug in 0 into the function, then you're going to get 0. That doesn't really help us. That verifies that this is an infinite limit, so we know it's approaching 0. So that's good. But the problem is that doesn't help us determine what the sign is. So note, do you see how we know that we're approaching a positive number on the top? Well, now we do know that this is infinite because we have a constant 4 over 0. But we don't know whether it's positive or negative. Normally when we have a fraction, if we have like 5 over 7, that means the result is going to be positive. If we have negative 5 over 7, we know the result is going to be negative, right? Positive, negative. If we have negative 5 over negative 7, we know the result is going to be positive again. Well, that's what's going to help us determine if it's in positive or negative infinity. So the question is how do we know what it's approaching in the denominator? So what I normally do is I pick a number that's really close to a. So a is 0 in this problem right here. So I pick a number that's really close to that on the side it's on. So this is the positive side of 0. So I usually pick a number like 0.1. Don't pick 1. That's a mile away. Pick a very small number. So if this is approaching, this is a positive 0.1, which is right to the right of 0. So that means the denominator, when I plug 0.1 in here, I don't want to do it physically, I just want to do it mentally, then it's approaching 0 and positive. Okay, since we have, to begin with, a number, a constant over 0, it's an infinite limit, but now since we have a positive over a positive, that means the result is positive infinity. So as I said before, not always getting it in the beginning. You might look at this right now and be like, okay, I think I get it. You might be looking at this and be going, whoa, like what's happening right now? Either way, you're going to, as we go through this, usually students start understanding it when we get down here, just from previous semesters. But just, I'm going to keep on going, making sure to point out the procedure that you're doing. So again, this one here is from the left side of 0, right? Left side of 0. So what are we doing, basically? We're isolating the 4 plus x and the x. So what is a number that's immediately to the left of 0? It's negative 0.1 is right there, right? So what would happen if I hypothetically plugged in 0 or a number close to it on the left side into the numerator? We would still be approaching, I'm going to change it to APPR to save space, approaching positive 4. Okay, that wouldn't change. It's still going to be a number right next to positive 4. But in the denominator, we're still approaching 0. And, well, if we plug in this value here into the x, what type of number is it? It is negative. So that means, yes, we have an infinite limit. It's a constant divided by 0, but we have a positive over a negative, which means that the result is going to be negative infinity for this problem. What is the two-sided limit, which is here? It does not exist because we have infinity and negative infinity. Okay, so again, students often will struggle a little bit with the first sets. Why? Because there's only a single x in the denominator. So what will make it better usually when we start the next line of problems? So let's look at the same exact procedure for what we need to do here. So for 4a, it says find the limit as x approaches 2 from the right of 1 minus 3x over x minus 2. Now note, if we immediately plug in 2 into this equation, we get 1 minus 6, which is negative 5, over 0. So we know a constant over 0 creates an infinite limit. The key is we must use the procedure I'm about to show you in order to do it, to figure out whether it's positive or negative. Now, a lot of students can do it mentally, and if you can do it mentally, then go ahead and do it. But make sure that you completely understand it before going in that direction. So we have our function we're going to analyze. What is a value immediately to the right of 2? Well, let's pick 2.1. Okay? So the top, we already said if we plug in 2, we're approaching negative 5. So 1 minus 2 times 3 is negative 5. But what about the denominator? Well, we know it's approaching 0. That's why we know it's an infinite limit. But is it positive or negative? So how do you determine that? You take the 2.1 and you hypothetically, mentally, put it in there, and what kind of number do you get? You get a positive result, which means we're going to have a negative over a positive, which creates negative infinity. What about this guy over here? So the numerator doesn't ever change here when you do the same problem. It's still approaching negative 5. But what is a number that's immediately to the left of 2? Well, it actually is 1.9. So what's happening in the denominator? We're still approaching 0. It's going to be right up against 0. When we do this, 2 minus 2 is 0, or numbers close to it will be near 0. But what type of sign is it? Now take the 1.9 and just quickly take a peek. 1.9 minus 2 gives you a negative number. Negative. So that means we have a negative over a negative, which means we get a positive. And because these are not the same, this is, again, the two-sided limit does not exist. Okay, let's look at number 5. So we want the limit as x approaches 5 from the left side of the following quantity, or function. This is obviously getting a little bit more challenging. So what does that entail? So we know that when we plug 5 into the numerator, we get approaching 6. specifically positive 6, right? And if we plug 5 in the denominator, we get approaching 0. But we need to know what side of it's approaching. So what do? We pick a number that's to the left of 5, which is very close to 5, 4.9. So we go over to the bottom of this. The numerator's fine. We already know it's positive. We need to know whether this is positive or negative, or what side of 0 it's on. So we go into here and we put 4.9 minus 5 in our brains. What type of number do we get? We don't care what the number is. We only care that it's positive or negative. So what type of number do we get? We get a negative number. But what do we need to do with that negative number? We need to cube it. When we cube a negative, what type of number do we get? We get a negative number. So that's what makes this more challenging, is you have to do a little bit of mental math to figure it out. So a negative times a negative is a positive, times a negative again is a negative. So look what we have. We have a positive over a negative, which gets us negative infinity. So worth noting, like on exam situations and other, I don't normally give you all of these, like all 3 in a row. I usually just give you a random singleton value problem like 5, because as you see, when we go to 6 here, it's a completely different problem. So worth noting. All right, so let's take a peek at this function. We're going -1 from the positive side. All right, so again, if we plug in -1 in the numerator, it looks like we're approaching -3. All right, so that's good. Approaching -3. Okay, if we plug -1 into the denominator, we get -1 times -1 plus 1, which is 0. So we are approaching 0. Here's the issue, though. We don't know whether it's positive or negative, so that's where this comes in. So in this, you have to be very careful. So if you're at the number -1 and you go in the positive direction, what is a good test number? It's actually -0.9. So when I normally teach this in class, students will say -1.1 because their number lines are always a little messy on the negative side. So it's actually -0.9. So if you plug in -0.9, you have to be careful. Why? Plug it in here and get a negative number. Plug it in here. -0.9 plus 1 is a positive number. So a negative times a positive gives you a negative. So a negative over a negative gives you positive infinity. Note, on exam situations, usually, we'll see how it is in the remote environment, but normally I give these types of problems. So be ready for them. These are not too easy up here. This one probably too easy, but these aren't bad, these problems. But I tend to give more advanced ones because it's calculus, and you should be able to follow the positive and negative values throughout this with squares and cubes and multiplying and all that. So be ready for something like that. Okay, so number 7 is a bit of a doozy, and that's why it has a star on it. So let's say we're trying to find the limit as theta approaches 0 from the left side of the cotangent of theta. Okay, so the first things first. Normally, you're not required to find actual cotangent of theta. Most students don't even know what the graph looks like or can draw it accurately right from scratch, even if you took pre-calculus. So, and there's an issue here. Look at all the other problems that we did. They're all what type of function? They're all rational functions. This isn't a rational function. This is just a function, trig. So what we do, just to make this rational in nature, is we want a trig identity. So you've already had the trig identity that tangent is sine over cosine. So cotangent is going to be the other way around. Cosine over sine. So when we change it to this, we now have a rational function. And if we plug in 0 to this rational function, let's see what happens. Okay, again, what are we dealing with? We're dealing with the unit circle, right? At 0 radians, we have a coordinate of 1, 0. Cosine is always the x, which is 1. So this is approaching 1. Positive 1. And the sign is always the y-coordinate, so this is approaching 0. But what's the issue? We need to know whether it's positive or negative. That creates a whole different scenario. Why? Because we don't really want to use like 0.1, negative 0. Whatever. We'd rather like stick to trig. So what I do is I actually use the graph to help us out. So most students know that the sine graph looks like this, just like the cosine graph looks like this, because cosine goes through 0, 1, and sine goes through 0, 0. So what are we doing? We're actually theta is actually approaching 0 from the left side. So look at our graph. If we approach 0 from the left side, what type of heights are we actually going through? What types of heights? Well, everything around here, or what types of values of y, if that's easier, all the values approaching from that side are negative, which means that this is negative. So when we look at this problem, we go, oh, okay, so this is positive and this is negative, which means this is negative infinity. So if you were to look at the general graph of cotangent theta, which is one of these suckers with things, asymptotes on them, you would find that if you approach 0 from the left, let's say this is 0, you would be heading towards negative infinity. So that's essentially the idea for this in terms of what you would be doing for this method. It actually takes practice. So students try to find shortcuts. The only shortcut that you should be using is basically mentally plugging this value in. What do you not want to do in any way humanly possible? Watch. Okay, I'm going to write it over here. Okay, what students will do with something like, let's say this problem. So they'll pick this number 0.1 and then they'll start going, oh, this is equal to 4, the limit of 0 is equal to this over this, and then they'll do 4.1 over 0.1, and then they'll do this math, and then they'll get some answer. Don't do that. That is not what you do. This method is it's basically an approximation method for what you're approaching. It is not a literal method for plugging in numbers. Do not do this. If you do that, you're basically going to put yourself in the automatic wrong answer mode. So don't do so. This is just for approximation with what's going on as we head to the next section.